So welcome back. Today we'll be discussing the quantum search and we'll introduce the Grover algorithm. The topics of today's lecture will be to introduce the problem of quantum search and to introduce the technical elements such that the Grover diffusion and the Grover iteration that will be required to solve this problem in a quantum mechanical fashion. We will then give an interpretation from geometrical means of the Grover algorithm. Now, the problem of searching entries in a database is actually a very common problem in classical computing. What we want to do is to find a unique entry in a database that is unstructured and contains the elements. Classically, we need, on average, d over 2 call of the database to find the correct answer. And this is because if you are very lucky, we can find the entry on at the first time we call the database. But if you are unlucky, we need to call all the entries of the database to find the correct element. Today we will discuss how, with quantum mechanics, we can get the correct answer in order root of the call of the database. And this produces a very important quadratic speedup that for quantum computers. The way to do that is by using Grover's algorithm. Now, Grover's algorithm takes as an input an n-qubit registry that is describing the database of dimension d to the power d that is equal to 2 to the power of n. And we also need an extra qubit that will be ancillary. So one extra qubit initialized to the state 1 that is shown over here. The circuit that performs Grover algorithm is shown below. And now we will see exactly how this circuit works. I also want to emphasize that this shorthand notation here means that we cut the circuit and we repeat it a bunch of times. And in particular, we need to repeat this step roughly root of d times. Now, let's see step by step what this circuit does. The first step is a rather common step at this point. We Hadamard transform the qubit registry, which is initialized in the state 0. Once again, this is the decimal state 0, so all the n qubits in the registry are initialized in 0. And we also apply an Hadamard gate to the state 1 of the ancillary qubit. Just like the Deutsch-Jozsa algorithm, the output state will be given by the superposition with equal probability of all the possible qubit registries and all the possible vector state in the qubit registry, tensor with the minus state of the ancillary qubit. The next step is also a common one, and we also have seen what happens. And what we need to do here is to call an oracle. Now, just to be more clear and to understand why this is related to a quantum search, let us revisit the concept of oracle. The concept of oracle, as we saw before, essentially considers a registry of n qubit x, initializing a state x, and passes it through. And what this unitary function, this oracle, does is that to an ancillary qubit, here initialized in a state y, it adds a function of the registry state modulo 2. Suppose that we choose this function such that the function is 1 only for a certain registry input and is 0 for all the others, then we can interpret this oracle as a black box that only marks certain desired input strings. This is essentially what we want in our quantum search algorithm. With that clarified, now we can go back to our quantum circuit. And we know the result of what happens when we apply this oracle to this particular initial state. In particular, the phase kickback trick for this input will give us back still a coherent superposition of all possible states, but now with a phase that will depend on the function of the input state x. Now, to be more specific, if we take this function to be 0 for all the entry but the one entry that we want to find, what happens explicitly is that all this state, this state will be given a plus, a combination of all input state that are not wanted with a plus sign, and will give a minus sign only for the state that we want to find. Now, to get something useful out of this input state, we need to apply another gate to the qubit registry. This is a new gate that we haven't seen before, and it's called Grover diffusion. And it's this, this box called D. Another name for the Grover diffusion is the inversion about mean, and we will see why this comes about. The Grover diffusion, in fact, takes an input state psi of 0, a general input state psi of 0, and outputs a state psi of 1, according to this rule. In particular, it takes 2 times this state phi and subtract the identity. It's a projection onto phi times 2 minus the identity. The state phi is just a coherent superposition of all possible states in the registry. Now, before try to understand what this does, let us see how this circuit can be implemented, this Grover diffusion can be implemented. And in particular, one can think about this, this quantum gate as an Hadamard transform followed by a phase shifter where essentially all the state gets a minus sign except for the 0 state. And then we finally also Hadamard transform the output state. So this decomposition is one way that we can use to understand what the Grover diffusion gate does. So to see what this Grover diffusion operator does, let us be more concrete and let us see mathematically what is the effect of this D operator on an arbitrary input state psi of 0. That is an arbitrary input state where we take a general combination with coefficient C of Z of all the possible input strings capital Z. Now, when we apply the operator D that we just defined, the output state will be given by this formula. So essentially, will be the projection onto the state phi times 2 minus the identity applied to this state. Now, with a little bit of math, we can convince ourselves that this projection will just evaluate 2 times the mean of the coefficients of this state. In particular, the mean of the coefficient is defined as the sum over all the coefficient divided by the dimension of the Hilbert space. This is the reason why this operator is called inversion about the mean of the state. So let us see now what happens after the first iteration of the circuit. The input state of the diffusion operator is given here, and after applying the diffusion operator on this input state, we just have to invert about the mean of the state. This means the mean of the state is given by this particular value over here. So it's 2. The mean of the state is 1 minus 2 over D, and we need to multiply by 2. Now, we can also interpret this operation not just as a function of any x, but also splitting explicitly between the unwanted strings capital X and the wanted string capital X of capital X naught. In this case, we see that the unwanted string gets a factor of 1 minus 4D, while the string that we want to find, x naught, will take a different factor. 3 minus 4 over d. Now, to interpret what just happened, it's convenient to introduce a separate type of, a slightly different type of notation. In particular, we will introduce a quantum state capital Y that is a sum of all the unwanted string with a proper normalization, and we will have a separate orthonormal state that is the target state x of 0. So let's reinterpret the step that we just took in terms of this new basis. Now, the Hadamard transform, we saw that produces a coherent superposition of all possible input states, wanted or not wanted. If we want to rewrite it in terms of those two states that we just introduced, then we need to just be a little bit careful with the prefactor. In particular, what we do get is that the prefactor are given by d minus 1 for the output for the unwanted state, root d minus 1 over root d, and just 1 over root d for the wanted state x naught. Now, this is still not particularly clear, so what we will do now is just to introduce a little bit of trigonometry. And in particular, we will introduce an angle theta. That is just the arctangent of 1 over root of d minus 1. This is very convenient because now we can rewrite this formula in terms of cosine and sines. And in particular, we see that the output state of the Hadamard transform will be a cosine of this angle theta of y, tensor product, the minus state of the ancillary qubit, plus sine of theta of x naught, tensor product minus of the ancillary qubit. So let us see now what happens when we apply the rest of the Grover algorithm to this input state. The function of the oracle, u of f, is very easily captured because the only thing that the oracle does is changes the sign of the wanted string. So essentially, the output state will be given by the cosine of y tensor minus the sine of theta of the wanted string tensor, the minus state of the ancillary qubit. Now, to be more precise, this actually can be can be understood because the function, the unitary function, the unitary oracle u of f does nothing on the unwanted string, but does flip the sign of the phase of the wanted string of x of 0. So let's see then what happens by the diffusion operator, the Grover diffusion operator. We can still rewrite this in terms of the unwanted state, the sum of the unwanted state y and the wanted state x of 0 in this way. This is, however, still not particularly insightful. So what we'll do now is try to introduce they try to introduce our angle theta back in the picture. To do that, let us consider the action of this diffusion operator on the state y and on the state x0. We can easily see by the definition of the diffusion operator that the output will be given by this formula. So it will create a superposition of y and x0. This is still not insightful enough, so what we will do now is explicitly rewrite it in terms of the angle theta. And in particular, it turns out that by using trigonometric relation, that the output state can be written in this form. Essentially, we will have a cosine of 2 times the angle theta and a sine of 2 times the angle theta. When the diffusion operator is applied to the y state, we will have the positive combination of them, while we will have a minus sign when the diffusion operator is applied to the state that the wanted state x0. Now, with this in mind, we can also try to rewrite this output state of the diffusion operation at this stage in terms of the angle theta. And it turns out that this can be just rewritten very simply as a cosine of 3 theta plus a sine of 3 theta x of 0. So we can interpret the Grover iteration as a rotation. As we saw, by combining the Grover diffusion times the oracle call, we can actually construct a rotation matrix of that rotates the state y and x0 by an angle of 2 theta. When we apply this rotation matrix, or the Grover iteration, to the initial state, which was the combination of cosine of theta y and sine of theta x0, then what we do get at the end is exactly what we show. So it's exactly cosine of 3 theta y plus sine of 3 theta x0. This gives actually also a very neat way of interpreting what happens after k iteration of the Grover algorithm, so of the Grover step. Because after k iteration, essentially what we do is just apply k times the rotation matrix on these states. And what we do get at the end is just a rotation of 2k theta of the initial state. This means that the final state after k iteration of the Grover algorithm will be just the cosine of 2k plus 1 theta times the unwanted state vector y plus sine times 2k plus 1 theta of the wanted string x of 0. So this gives already some very insightful result, because the probability to be in the correct state at the end will be just given by a sinusoidal function of 2k plus 1 times theta. If we plot this probability as a function of the number of iteration k, then we see that this probability will reach a certain, and approach 1, and then will keep on rotating. So what we want to do for the Grover algorithm is we want to find the number of iterations that will guarantee that we are finding the correct answer. And this is given after an iteration k star that is given by pi over 4 times theta minus 1/2. For this iteration, then we will get the correct answer with probability of 1. However, there are some caveats here. In particular, the fact that the number of iteration is just an integer number. So let us see what happens when we take the limit of very large databases. In this case, the angle theta can be approximated as just the root, it's just 1 over the root of t minus 1. This means that the perfect or ideal number of iteration will be given by the integer part of pi over 4 times d minus 1 minus 1/2. And d minus 1 is of course under root, which means that the number of iterations that one needs to take are of order root of d. For this specific example, this means that for n equal 10 qubits, which means a database of 2 to the 10 number of states, a number of entries, we just need roughly 24 iterations. So let us now see if we can have a more intuitive interpretation of what has happened during the Grover algorithm. And for doing that, we will introduce a little bit of geometry. And we'll reinterpret this algorithm as just a rotation in a more visual way. We will start by considering the vector space that is spanned by the orthogonal vector y and x0, that I remind you are the state vector of all the unwanted state, the combination of all the unwanted state and the state that we want to go and we want to reach. The initial step after the Hadamard is just a slightly rotated state in this vector space, and is the state phi. Once we apply the oracle, we essentially just invert the state about the axis x0. So essentially, from being rotated to theta, it gets to the state uf of phi, which has an angle minus theta. Then we apply the diffusion operator, and as and the diffusion operator is essentially the inversion about the mean, and or in other words, is the inversion about the state vector phi. So what we do now is we invert, we rotate, we flip the state u of f about this axis, and we essentially pick up an extra 2 theta angle, resulting in the state d u of f of phi, which, as I remind you, was 3 theta rotated with respect to the original coordinate system. Then what we do is we keep rotate until we reach the wanted state x naught. And this can be done in order of root of d times, where d is the dimension of the database. And this gives a quadratic speedup for the search, for the quantum search algorithm.